So today we'll look at one-sided derivatives. So by definition, and by the way, this is not something that the AP exam ever explicitly asks about, but sometimes it kind of helps to understand this to be able to explain things that they want explained in the next section. So the limit as h approaches 0 from the right of f of a plus h minus f of a all over h is the right-hand derivative, I should say, of f at a. And then we can also do the left-hand derivative of f at a. Now, if the right-hand limit and the left-hand limit do not agree with one another, then the limit doesn't exist. So let's look at this one. For this particular one, we are going to show, unlike the one that was on last night's homework, here the left-hand derivative and the right-hand derivative both exist, but there is no derivative at x equals 0. So, for the left-hand derivative, we're going to take the limit as h approaches 0 from the left of f of x plus h minus f of x all over h evaluated at x equals 0. And part of the reason I'm doing the evaluation bar on that is because there's 0 in so many places it can get confusing. I think this is a real concise way to write, this is what I'm doing. So that'll be the limit as h goes to 0 from the left. So we're looking at the x squared part. So that'll be 0 plus h squared minus, and here this is going to be f at 0. What is f at 0? 0. All over h. So that'll be the limit as h goes to 0 from the left of h squared over h, which is the limit as h goes to 0 from the left of h, which is 0. Then the right-hand derivative will be the limit as h goes to 0 from the right of, I'm going to take the time to write this out, f of x plus h minus f of x all over h evaluated at x is equal to 0. That'll be the limit as h goes to 0 from the right. Now, as h is going to 0 from the right, we're looking at the 3x values, right? So that's going to be 3 times 0 plus h minus f at 0, which is still 0. All over h. So it'll be the limit as h goes to 0 from the right of 3h over h, which is the limit as h goes to 0 from the right of 3, which is 3. We have two different slopes here. The slope from the right and the slope from the left do not agree with one another. You may wonder what this looks like. You know what? I think I'll pull that up actually. Let's do this. I'll get to show you one of the reasons why the NumWorks calculator is better than the calculator you're using. Let's go full screen on this. All right. So when you're graphing on this thing, one of the built-ins, it says add an element. If you click on OK and go over to templates, it's got all these built-in things, most of which I don't care about. But right there, we can do piecewise functions, which is way easier. I think I showed you guys how to do that the other day by doing 1 divided by the restriction, which is, I mean, let's face it, that's kind of clunky. So what was the first one? Was it x squared? Yeah. All right, so let me back over this. So I just want x squared, and it was less than or equal to? Now I have to remember how to do this part. Oh. You just type equals, which is somewhere on here. I'm used to doing it on the keyboard because I've done it so much. It's in there someplace. I just can't see it. It's too small. And then for the other one, I wonder if I do equals if it gets rid of, well, get rid of it. Huh. And the other one was 3x, right? Still getting used to how this works on this. And then I'm going to go back to the top, and I'm going to show the graph. This is really, really nice because it picks a window that shows you important features. And you can see what happens down here at 0. Now, I'm going to change this to kind of zoom in more on that. So what I can do is I can go up, instead of auto doing it, I can go, yeah, I want to pick my values of x. And I'm just going to go, you know, from like -2 to 2. And then for the y, I don't know, I'll go -2 to 6 or something. And go, yeah. Oh no, I don't. Cancel that. What the heck? You can see it a little bit better here. See how the slope as we enter from the left flattens out, looks like 0, and then all of a sudden it goes doink, right? It doesn't make sense to say that there is the slope of the curve at this point, because over here the slope looks like it should be positive, over here it looks like it ought to be 0. The two disagree with one another. Okay? All right. So if by the way, you ever want to play around with this calculator, you can use it online, and um, if you ever want to borrow mine, you're welcome to do it. Okay, I'm not advocating that you rush out and buy this calculator. If it was for statistics, I would actually say yes, you should buy it. It's way easier than what we did with the TI. And at this point, I have two that have the NumWorks and two that have the TI. And we're not very far into the year, and they're already going. Some of the other ones are going, yeah, I should get me one of those. Anyway, let me give you tomorrow's notes. We won't do all of this, but we will do a little bit. Oh, you've got lots of time. All right. So the next section is the idea of differentiability, which if you could figure out a way to do that in Scrabble would make quite a lot of points perhaps. Unfortunately, you don't have that many letters. You would almost have to have someone do different, and then you had the rest to make it differentiability. Anyway, sorry, it always strikes me as that's a really long word. So remember that if the right-hand limit at C is not equal to the the right-hand derivative at C is not equal to the left-hand derivative at C, then the derivative at C doesn't exist. There are multiple forms that you'll see this in graphically. So one of them is a corner, like so. And that's kind of what was happening on the one we just looked at. You had this corner where the left-hand derivative and the right-hand derivative aren't the same at x equals c. Okay? Some people call this a sharp point, which always struck me as, I understand what you're saying, but